In part 1 of the video, we looked at the modeling process in detail. In part 2, we will focus on some of the outcomes of this model, look at the validation results, and I also wanted to focus on the adjacency matrix that is created as part of the modeling process, which can be quite useful in our coordination study. So this is the complete electrical feeder model, the outcome of our modeling process. The left side is the OpenDSS model and the right is the SIMDIST model. The green circles here indicate the location of the PV generators. The different colors of the lines, both in OpenDSS and SIM, they correspond to the actual phases, phase A, B, or C. So clearly the model includes the secondary side of all the transformers and extends all the way down to the individual customer loads. Okay, so next I wanted to show some of the outcomes of this from MATLAB following these various modeling process that I described. So I'm going to look at some of the text files that MATLAB created to in a format suitable for OpenDSS to do various OpenDSS workflow analysis. So this is all part of the protection analysis toolkit that you should have. So it has all the GIS data information, the various DSS files that it created, most of the M files that was used to create those outputs, and some of the data files as well. So all of these, the protection, coordination, lateral views, recloses, these are the things that will be running in the next few videos to go through the coordination analysis. But right now I just wanted to show some of the DSS files. So let's look at, for example, the bus coordinates. So this only has the bus ID, the node ID, and its XY coordinates. So this includes all the buses or the nodes in the system, and you can see that it has something like about 8,000 8,400 nodes. This includes all the primary, secondary nodes, all the fuse terminals, the switch terminals, all of them included. So similarly, if you look at the lines.dss, that has all the lines or the section information. In this case, just the ID and the length of each section. But if you go to the line codes.dss, that has the all the characteristics of each of the line type. So it has the resistance, the various positive and zero sequence impedances for each of the single phase, two phase, and three phase line and conductor types, including overhead and underground. And in a different place, we also have the triplex line information, which is like the triplex line codes that corresponds to those triplex lines, and transformer triplex has the information on the three winding secondary distribution transformers. Similarly, if you look at for example this loads updated.dss, that has the information on the loads at each of the transformer secondary, like the kilowatt and the power factor of operation, and this has been determined from the method that we use called the zone division analysis. Other interesting files, the PV, for example, the PV meter PV shape files. So this can be used for the time series analysis. So this has, I think this is an hourly information so for each of the time steps, it has the kilowatt output, and the power factor is assumed 1 for all the PVs. So similarly, we have the load shapefiles, meter load shapefiles would be useful for time series analysis, and the loads at each of those intervals, whether it is 1 minute time resolution or 1 hour time resolution, that is entered here. Okay, these are some example results from a time series analysis in OpenDSS. So the green waveforms in each of these plots, those are the simulated line to neutral voltage at this DAS5 location. And these are all compared with the actual field measure data from the DAS5. DAS5 itself is somewhere in the middle of the feeder. So we're looking at the voltage at the midpoint of the feeder. And on a complete day, September 25th, 2012, and this is a time series simulation at 1 minute resolution. So clearly you can see that there is a very good match between the simulated green and the measured red waveforms. In fact, the RMS error over the complete day is shown here. For example, phase A has only 0.027 kilovolt error over an average of around 7.5 kV. So that corresponds to less than 1% error, maximum of 1% error, probably in phase C, which is what looks slightly off compared to the others. So the 1% error gives us very good confidence in the accuracy of the models. This is another time series result. This is the measured and simulated kilowatt at the DAS4 location, again at 1 minute interval over a day. So again, it's a good match between the black and the red waveform, which are the simulated and the measured kilowatt at DAS04, with the actual conditions, with all the PVs included. So clearly this drop here in kilowatt consumed from the grid is because of the large PV generation during this day period. So one good thing about simulations is we can do a lot of what if scenario analysis. So in this case, these blue dotted lines here, they correspond to situation where we remove all the PV systems. So this would be the new load drawn from the grid in the absence of all the PV generators, and then we can get the corresponding voltage profile and compare that with the voltage profile with PV. The last topic that I want to cover in this video is this adjacency matrix, which is very useful in our protection coordination studies in the later videos. So the adjacency matrix is created as part of our formal feeder network model development that we discussed, and this matrix has critical information on how the nodes are connected and the relative position, mainly which is upstream versus which is downstream. So that is extensively used in our protection coordination study to determine what all faults we need to apply for a given coordination, fuse to fuse or fuse to recloser. We need to know the information on downstream versus upstream. And the matrix can also be used to identify all the protection devices that needs to operate from the fault location up to the substation, and therefore it also is useful in verifying their proper coordination. The adjacency matrix is also used in the model reduction, many model reduction techniques, and therefore useful in transient studies. The adjacency matrix is typically a very large matrix. For the Sandvik feeder, it is 2124 by 2124 matrix. Okay, since our feeder is fairly large and our model is quite complex, it may be difficult to fully comprehend all the methods and algorithms that we'll be seeing for protection coordination in the next few videos. So I will be describing many of the concepts and the algorithms on this much smaller example feeder, and then show the codes corresponding to the actual larger Sandvik feeder, and show the results corresponding to that. So this example feeder has one substation relay, and just one recloser. Multiple lateral fuses, both upstream and downstream of the recloser, and multiple transformer primary fuses, okay? and of course all the loads. So here is the adjacency matrix for this very small example feeder. So if you count the number of nodes, it has 21 nodes. So therefore the adjacency matrix M would be a 21 by 21 matrix. The rule for the adjacency matrix is the element Mij on the ith row and jth column is 1 only if the node I is directly connected to node J, and the node I has to be upstream of node J. Okay? So for example, if you look at the first row corresponds to the node 1, so the second entry is 1. So that is because node 1, which is here, is directly connected to node 2, and node 1 is upstream of node 2. Similarly, if you look at the row 2 corresponding to node 2, it is connected, even though it is connected to 1, this entry is not 1 because node 2 is not upstream, it is actually downstream of node 1. Okay, therefore it is just a 0. But if you look at the third column corresponding to the child node 3 for this node 2, so here it is 1 because node 2 is connected to node 3 as well as it is upstream. So similarly, you can see for any other node, all the entries correspond to whenever they are upstream of the corresponding child node. From the adjacency matrix, we can also create the we can trace the path from any node all the way to the substation node, and enter all the upstream nodes going from the given node to the substation, and those are entered under a node cell in the in our MATLAB code, which I will demonstrate shortly. So if you come back to our original feeder, so which was 2124 nodes, so the corresponding adjacency list is right here. Okay. So that is okay. So that's 21 by 21, 2124 by 2124 matrix is shown here, and so if you look at the first entry, which is the node 1, that's not really related to the number. The node number is not related to the location of the node in the feeder. It's arbitrary. So the node 1 is connected to node 2, and in this entry in MATLAB, instead of putting as just 1, we just write the node number itself. So the entry node here, entry 2 here, means that node 1 is connected to node 2, and node 1 is actually upstream of node 2. Okay. Similarly, if you look at this row here, node 8 is connected to 7, and this entry here represents that node 8 is the one which is upstream, and we just put the node number of the dotted node here. Okay. Same thing everywhere else. So that is the adjacency matrix for this larger feeder, and so then we can take a look at the node cell, which is right here. So 2124 by 175 cell. So what this means is, if you look at, say, node 1, so this row lists all the nodes upstream of node 1 when we trace the path from node 1 to the substation. So it goes through 432, 594 all the way to the substation node. So if you keep going, so it would end when it reaches the most upstream node. Okay, so row 1, so the last few entries are 1934, 1935, and there is no further entry. So 1935 is probably the most upstream node, the substation node. Similarly, row 2 also has all of these upstream nodes and eventually ends at 1935. The other, for example, node 5 goes. So if you look at the row 1935, it should not have any entry because we expect that to be the most upstream node. So 1935 is right here. So clearly there is no entry here. 1934 has just one entry. That is probably the second most upstream node. It's only connected to 1935, and 35 is upstream of that, and there is nothing more upstream than 1935. So this node cell matrix can be very useful for several purposes. For protection coordination, we will know for a given fault we can trace all the upstream protection devices, fuses, recloses, till we reach the substation relay, and so this can be used to determine the coordination for different types of faults. Similarly, for model detection, say if your objective is to combine all single phase loads, club them together and connect the combined load at the nearest three phase section, once again this node cell can be useful for that. Okay, so we have briefly gone through the various steps involved in the feeder network model development, and we also saw some validation results. And so in the next 2-3 videos we will use this framework, this model, to study the protection coordination of various fuses, recloses and relays under different PV penetration levels.